Right, so today we are going to start the radioactivity part. Right, so first, this incident was discovered by this scientist called Henry Becquerel in 1896. So he discovered that the uranium compound. So he had a uranium compound placed closer to a photographic film wrapped in a black paper, and he observed that. So there's a photographic film wrapped in a black paper, and nearby there is a uranium compound. So he spotted that there are some variations, like dark spotted on the film, on the photographic film. Then he did some different. So he did some experiment at keeping the uranium that you represent the uranium uh, particle element, and so there's a this is the photographic film. Yeah, this is the photographic film. And so he kept different types of object like cardboard and wood or some metals in between this uranium and photographic film. Right? So he was trying to block some sort of things coming out from uranium. Right? So but he observed for uh, almost all the objects or layers that he kept in between uranium and photographic film, the same incident happened. And no matter it is wood or cardboard that he keep in between this particle uranium and the photographic film, same thing happens. Right. So later, the famous uh, female scientist actually in that era, uh, in where this century, called Marie Curie, he first identified and systematically discovered uh, this phenomena or this ray, some amount of some type of rays coming out from this uranium as uh, radioactivity, right? So he named as radioactivity this this phenomena, right? Radioactivity. Right? And these rays are different from X-rays. Unlike so, if it is X-rays, if a lead sheet is kept in between photographic film and uranium, definitely the X-rays would be absorbed. That we learned previously. But here that also does not happen. So these are different from X-rays as well. And most of the things that were known. So she named these uh, phenomena as radioactivity. Right? So radioactivity. Uranium emits some radioactive element. So we say the uranium. Uranium. Uh, yes, uranium. This is the most commonly known uh, uh, element, right? Uranium. And there are some others as well, like polonium, radium. Right? So different uh, types of elements are there, which exhibit the same behavior of this radioactivity. Right? So normally uh, carbon and those carbon, sodium, maybe potassium, those kind of element does not exhibit this uh, behavior called radioactivity. Only some specific elements in the periodic table show this incident, right? Phenomena called radioactivity. They exhibit natural, right? Without any external interference, they exhibit some type of radioactive element. So these are called radioactive elements. Radioactive elements. So which are not, which are actually harmful. Mostly these radioactive elements are harmful to humans. Radioactive elements. Right? Radioactive elements. Like in nuclear bombs as well, inside the nuclear bombs, the radioactive elements are incorporated. So when it blasts, it goes out and do a very bad, huge damage to surrounding. Right? So very dangerous as well as very useful as well. Radioactive element very useful. In the case of nuclear power plants are run by this method and radioactive elements. So in that case, it is very useful. But when it comes to nuclear bomb or something, it is very dangerous. So there are advantage and disadvantage of this radioactive element of this yes, radioactive elements. And so this Marie Curie is the Marie Curie. She won the Nobel Prize as well in 1903 for this discovery of radioactivity. Right, so to date, around 40 radioactive elements have been identified. And normally it is said that if the atomic number, right, atomic number greater than 82. Atomic number means, so if there's some element, Z A. Right, so this Z is called the atomic number. Normally, if the atomic number is this notation is a standard notation. So this represents the number of photons, and this A represents number of photons plus neutrons. Number of photons plus neutrons represent A, and number of protons represent Z. Uh, Generally, if the atomic number is greater than 82, those are called radioactive elements, and they are unstable. And they are unstable, like thorium, radium, thorium, some examples. And the most importantly, you have to grab here is they are unstable. They are unstable. That is, radioactive elements are unstable. That radioactive elements are unstable. They don't like to be in that state, which means they are unstable. They are always trying to come to a different level, now different uh, structure, right? They, like if we consider carbon, the carbon atom tends to be in its original position. That if no external force, external effect is applied on that, it would stay mostly as it is. But these radioactive elements always try to shift from the original state to some other state, which is more stable. Right? Radioactive elements are unstable, so they are always trying to shift to a more stable position. Radioactive elements. Radioactive elements are unstable. Radioactive elements are unstable. Uh, and always always tends to transform into a different element. Transform into a different element which is more stable. Different element which is more stable. Element which is more stable. Which is more stable. Is more stable than the previous element. Right? So there are uh, so when an element, radioactive elements transform to a different element. So it always emits some type of uh, particle or ray, right? Radiation, right? So when a radioactive elements transform to a different one, right? When a radioactive element transform to a different substance, different element, always it emits. Right? So, example, if say X is a radioactive element, and X is a radioactive element having Z1 and A1 number of protons and number of, so here A is Z is a number of uh, electrons, right? Number of electrons. A is the addition of number of protons plus neutrons. Addition of number of protons and neutrons. Neutron. So if there is a X element, is a radioactive element having Z1 and A1 of atomic mass number, and it would transform. So this is a radioactive element. Radioactive element. Automatically, right? Radioactive element, it would transform automatically without any external interference. It would transform automatically into another substance having Z2 and A2 of a different atomic mass number, having different atomic mass number, and would when during this transformation it would emit some amount of some type of particle or a ray, right? Particle or ray. In addition to that, after this transformation, it would emit a particle or ray. That could be anything, particle or ray. We cannot take over definitely particle or definitely a ray. Sometimes it emits after transformation a particle or a ray. So mainly there are three types of particles or rays that are been emitted from radioactive elements. Radioactive elements. Uh, Alpha, beta, and gamma. So there are three types of radiations which are being emitted from radioactive elements: alpha, beta, and gamma. Alpha, beta, and gamma. alpha, beta, and gamma. These are three radiations, mainly which are being emitted from radioactive elements. Right? So depending on the occasion, it might emit alpha particle. So or beta particle or gamma ray. So per one transformation, only uh, one alpha particle, either alpha or beta or gamma particle is emitted. Not all three at the same transformation. So first it would emit alpha particle, then it could emit the beta particle. Likewise, it could continuously go on until a stable. So this stable element is attained. So more stable element. More stable element. And there's another word as well. So this is the uh, first original particle element. It is called as parent element. Right? It is called as parent element. Then the output or the attained particle after the transformation is called as daughter. Right? So someone could say this is unstable element, or this could be given as a unstable element. So all the things represent same particle. If it is a parent element, it is corresponding to radioactive. If it is an unstable element, it is corresponding to a radioactive element. So if it is a daughter element, it is corresponding to the most stable element, which is obtained after the transformation, or it could be given as a stable element. All right. So alpha, beta, and now let's look at this about this radiations. Right? This radiation happens after the transformation of radioactive elements. So there are three: alpha, beta, and gamma. And so when an experiment is done, like here, so here there is a lead block. So it's a lead block and a radioactive element, radium. Small amount of radioactive element, radium, is kept here, so that this lead block, very thick lead block, thick lead block. We have to use a thick lead block. It's thick lead block because it's very thick. This radioactive elements would not be allowed to emit radiation onto these regions. Right? So these regions are protected. Otherwise, if we just keep a radioactive, it would emit radiation all around. It's all around all the directions around it. So this point of having a lead block in this manner, thick lead block in this manner, is to control this radiation. Now the radiation would only happen upward. That radiation would only happen upward, and here there is a magnetic field going in. Magnetic field going in. Magnetic field going in. And it is observed some particles. And so these particles, so if we consider alpha particle. So what has happened to the alpha particle? Alpha particle has shifted left, but in a slower manner than beta particle. But alpha particle has left, shifted left, or moved towards left, but it is not a very sharp turn. It is a very slow one compared to beta minus particle. And beta minus particle also shifted left, but it's a very sharp turn than alpha particle. And beta, uh, so this is beta minus particle, this is beta positive particle. And so mainly there are in beta particles there are two types: beta plus and minus, beta plus and beta minus, beta minus. And actually, after this experiment, it has been found that there are two types of beta particles: beta minus and beta plus. So they are having the same characteristic. Only difference is their charge. And this beta minus particle has negative charge, whereas beta plus particle has positive charge. And gamma rays, without any deviation, it just take its own straight line path. So from this experiment, what can be concluded? Can be concluded that so what is the requirement to be shifted? So what is the requirement to what is the requirement need to have in order to change the path? In order to change the path during uh, in a motion inside a magnetic field, right? There should be a current, right? Using Fleming left hand rule. Left hand rule. So definitely a force should be applied on these particles due to the magnetic field. So in order to happen that, a current should be no. You can use the Fleming left hand rule and try to apply it to alpha particle. Right? So B is into the whiteboard magnetic field, and the force is applied on the alpha particle towards left. Force is applied on the alpha particle towards left. Force. So which means the middle finger is pointed upward. Right? Middle finger is pointed upward. You can use your Fleming's left hand rule and try this. So middle finger would be pointed in upward, which means a current flowing upward. Current flowing upward. So current flowing upward, or we can say positive particle, positively charged particle moving upward is same as current moving upward. So these alpha particles are found to be positively charged. Right? Alpha particles are positively charged, whereas beta plus particles are also positively charged. Alpha and beta plus particles both are positively charged. So from this experiment, it could be found. And beta minus negatively charged. And gamma, what about gamma? It is neutral, no charge. And neutrally charged, no charge. And what is the reason that so alpha beta both they are both positive charge, but they are both positive charge, but alpha particle shift towards left slower than the beta positive particle. But what is the reason behind that? They are here also same thing. Right? Here also same thing. Instead of magnetic field, now electric field is applied from right to left. Electric field is applied here. The same situations happens. Alpha particle moves towards the negatively charged plate. Alpha and beta plus particle move towards the negatively charged plane, whereas beta minus particle move towards the positive plate. And whereas gamma ray does not deviate, it just have the same path as the original one. So here also this same thing is verified. The same observation uh, we obtained under the magnetic field is verified under electric field as well. Same thing happens. So here also alpha particle decays, alpha particle shift towards left less than the beta positive particle. The reason is, uh, you know, uh, an object having higher mass, is it easy to be is it easy to change the path of an object having higher mass? No, it is not. Right? Normally, if the mass of the object is higher, to change the path, we have to apply a more higher force on that. So here the reason is same. So alpha particles have higher mass than beta particles. So they are not being able to shift or shift towards some specific direction very easily. They are somewhat harder to shift. So that's why, uh, unlike the beta particle, that path is changed very sharp manner, but whereas alpha particle does not. Right? So alpha particles have more mass than beta particles. So uh, using so it is somewhat somewhat harder to change the path of alpha particle. Change the path of alpha particles to change the path of alpha particle using either electric field or magnetic field. Using either electric or magnetic field. Magnetic field. Right? So that's why alpha particles shift less than beta particle. Right. So these are some characteristic of alpha particles, beta particle, and gamma particles. Gamma particles, right? So these alpha particles are later be found that they are actually the nucleus of the helium particle, helium element. Right? Helium element, they are alpha particles are the nucleus. They have the same structure and characteristic of a uh, helium nucleus. Right? Helium nucleus. Not helium element, helium nucleus, only the nucleus part of the helium. So helium nucleus. So we can consider alpha particle uh, as helium nucleus. So helium nucleus means without without the two electrons, right? On the nucleus. So which means without two electrons, helium nucleus is positively charged, right? Positive two charge. So this alpha particles are positive. Alpha particles are positive charge, positive two charge. Alpha particles are positively charged, and mass is higher. And then mass is higher. Uh, Right, so each particle bears a charge which is twice the charge of proton, which is positive 2 charge. Right, so alpha particles. Velocity of the alpha particle is 0.06 times the velocity of light. It is slower than light, this alpha particles, the velocity of alpha particles, and penetration ability of alpha particle is 1 over 100. 1 over 100 of the beta particles, and 1 over 10,000 of gamma rays. Gamma rays. So penetrating ability means the ability the alpha particle would travel through any other medium, like a sheet or some wooden plate. The ability to travel, move, or penetrate through some uh, other barrier, right? So alpha particles having the less penetrating ability, because why? Its mass is very mass is not very mass is somewhat higher than beta particles and gamma particles. Mass is somewhat higher than beta particles and gamma particles, so the penetrating ability is somewhat high. So mass is higher of alpha particles than beta particles. Least is gamma. Gamma is actually not a particle, it is a ray. So having least amount of mass. So penetrating ability. So penetrating ability. Penetrating ability is highest of uh, gamma particles, then beta particles, then alpha particles. So you can we can understand that. So alpha particles are having the least amount of mass and the highest velocity. So the gamma particles travels with the velocity of light, and gamma particles travels with the velocity of light. Right, travel with the velocity of light. So having the highest velocity and least amount of least when they have a tiny particle, so they can move through any other object. And so they can slide through other material. Since gamma particles are very small, but whereas alpha particles are somewhat big, they are their penetrating ability is less, and so they would they would hit on other particles when try to surpass to any other medium, so their penetrating ability is less, and beta particles in between. And so beta particles, specialty about beta particles are beta particles act similar to electrons. Right? So alpha particles similar to helium nucleus, whereas beta particles are negative charge. Beta particles have negative charge and same as electron. So we can consider beta minus. As I said earlier, there are two types of beta particles. So beta minus, right? Beta minus, it is same as electron. It behaves similar to electron, and beta positive particle, it is called as positron. 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 Beta minus particle is same as electron. Beta positive particle is called as positron. Positron. So they are having both beta minus and beta positive particles have same mass. Only difference is the charge. The magnitude of charge is also same. Right? Magnitude of charge is also same, but beta minus it's a negative charge, beta plus is positive charge. Only sign is difference. Their velocity is also equal to approximately equal to velocity of light. Right. So then gamma rays having the highest velocity, the frequency range is 5 into 10 to the power 18, 3 in 10 to the power 21 hertz. Right, which is very huge, right? Very large, which is even greater than the frequency range of gamma rays are even greater than X-rays, greater than frequency range of X-rays as well. So these photons called gamma rays, these gamma rays have higher energy than X-rays as well. Frequency range is even higher than even higher than uh, even higher than X-rays, even higher than X-rays. So these gamma rays are very sharp, so they can penetrate to other medium very easy. Right, and that's a neutral charge. So it has some characteristics. You have to know, you have to have an idea that alpha particles have the higher mass than beta particles, and gamma particles has the lowest. The penetrating ability of gamma particle is the highest. Lowest is the alpha particles, and beta particles in between. Right. Then it was found, and it was found that these these radioactive elements, and we already know that these radioactive elements are unstable elements, and they would be transformed into a different element having more stable energy level. More stable energy level. These radioactive elements would be transformed into a different element having more stable energy level. And so let's consider some unstable particles or radioactive elements. Sample of radioactive elements. Let's consider sample of radio elements. So this is a sample of radioactive elements. So there are, let's say, n number of sample having n number of initial n n number of radioactive elements. Right. So after sometimes definitely these radioactive elements would be transformed to more stable ones. Let's say X. So one to in the right number of elements, and some are being transformed to Y, which is more stable. and plus radiation is emitted. Radiation, it could be either alpha, gamma, or beta. And radiation is emitted. Right? And it is been found that this phenomena, this transformation from radioactive elements to more stable elements emitting radiation is called as disintegration. It's called as disintegration. The transformation of nucleus into another nucleus through the emission of charged particles. And energy is called as disintegration. And most important thing is this is unaffected. Its radioactivity is unaffected by any external factor, such as temperature and pressure or any other factor. Right? Although you keep this sample at 0 degrees Celsius or 100 degrees Celsius, this radioactive decay process, radioactive or disintegration process happens in similar manner. Right? So this disintegration or radioactive decay, same thing. Radioactive decay, disintegration or radioactive decay. Radioactive decay happens in similar fashion no matter you keep this sample at 0 degrees Celsius or 100 degrees Celsius. And so this is unaffected by external factors, which is important. You have to keep it in mind. This radioactivity does not depend on the external factors like temperature and pressure. Right? So it's unaffected by external factors, and this is called as disintegration, this transformation of nucleus into a more stable one. More stable is called disintegration. And isotopes that we know actually from chemistry knowledge. The isotopes are two different particles, same particles, two different particles, same particle, but only difference is the number of neutrons. Number of neutrons. Same number of protons. That same number of protons, say A. There are two particles having same number of protons, but different number of neutrons. Z1 and Z2. So these are called isotopes. These are called isotopes. I think you know this one already. Right? So two different particles, two particles having same number of protons, but different number of neutrons. They are called isotopes. So there are radioactive isotopes as well. Right? So these are called isotopes. Nuclides having same number of protons. Same number of protons as well as has a different number of neutrons. Since the atomic number is same, they denote the same element, but mass number are different. Mass number is different. So they are referred as isotopes. Right. So now about this, now let's study what is the transformation happen under each of these radiation. Under each of these radiation. So first we would go for the alpha emission. So which is very easy actually, alpha emission. Yeah. So radium, for first we consider the radium element. Radium element has 226. So these you don't have 226 of mass number and 88 uh, atomic number. And uranium, in uranium, right? So in uranium, there are 238 uranium, 238 mass number, and 92 atomic number. 92 atomic number. Right. So when an alpha particle is decayed, this radium would be transformed to so this radium would emit an alpha particle. Alpha. So alpha, in alpha particle there are two protons and four total mass number. So this is the atomic number is 2 of alpha and 4 mass. Mass number is 4. So it will be transformed to this element, and the resulting would be so 88. So atomic number and mass number on both sides should be same. Right? Summation of atomic number and mass number of both sides should be same. So in left hand side, the atomic number is 88. In right hand side, we have atomic number of 2 already. So in order to go for 88, this should be 86. So 86 plus 2 is 88. Likewise, the mass number is on left hand side is 226. Mass number we have already on the right hand side is 4. So it should be 222. Right? So this is what happens in alpha emission. Alpha emission from radium. So in the alpha emission of uranium, yeah, what happens? So alpha, so one alpha particle is emitted, and it would be transformed to thorium, EH. So atomic, what we have to consider here is both atomic number and mass number should be same on both sides of the equation. So in left hand side we have 92 atomic number. So right hand side 2. We don't fill the go for 92 should be 90. Here 238 for 234. So pretty easy. So general expression we can write. So if there is a element having atomic number of A and mass number of Z, after the alpha emission of alpha particle to 4, always the atomic number would be less than the previous one. The mass number would be less than 4 less than 4. It's 4 less than the previous one. So this is a general expression. This is what happens in alpha emission, then beta emission, and beta emission. So we know there are mainly two types of beta particles. Uh, Two types of beta particles, beta minus and beta positive. And beta minus and beta positive. Beta minus and beta positive. And so here some special thing happens here. Special thing happens here. For example, uh, from the example, so example, let's consider thorium having 90 atomic number and 234 mass number, right? So it would be transformed to EA having so beta by emitting beta minus. Right? So in beta particle is electron is similar to electron. So the charge is -1. There are no protons, so neutrons. So 0 is a mass number, and atomic number is -1. So same thing we can do. Both the number of atomic number and both atomic number and mass number should be same on both sides. So here 90 -1. So fill the gap. This should be 91. And this is mass number does not change. So by emitting beta particles, mass number does not change. The important thing here is, in addition to the emission of this particle, beta particle, it emit another antimatter called anti-neutrino, called a neutrino particle. Right? This is the notation for the neutrino particle. A neutrino particle. So in order to comply with the energy conversion and the momentum theories, linear momentum, conservation of momentum, anti-neutrino should be emitted. So another example for uh, beta emission is beta minus emission. This one 0 sulfur and anti-neutrino. These are some examples. You don't have to remember any of these. Xenon. Oh, so here always the addition of the atomic number and mass number is same on both sides. Atomic number and mass number are same. And likewise, beta positive particles also emitted. Beta positive particle is also emitted. For example is similar fashion. Beta positive particle, only difference is now the charge is positive one and the mass number is same as zero. So it would be transformed sodium. So here the addition of the atomic number should be equal, so it should be 11. And this is 23. So now when beta positive particle is emitted, now in addition to that, it would emit a neutrino. Neutrino. Previously it was an antineutrino. Now it is neutrino. So see another example. And neutrino would be emitted. Right. And so in general, we can say in beta positive electron, in beta positive emission, let's go for beta negative emission, beta negative emission, like electron. So we have X particle, X element having A of atomic number, Z of mass number. So after beta emission, beta minus emission, what would happen to the what would happen? Always the mass number would not change. Atomic number would be increased by 1. And in addition to that, antineutrino is emitted. This is a general expression. Right? So here actually inside the elements, what happens? Inside the elements, so we can see here the number of protons. That number of proton inside the element is increased by 1. Yeah. Here, number of protons. Number of protons element is increased by 1. By 1. So inside the element, what happens? Right. So let's say so this is the X particle. There are P, P, N, N. And for example, let's say if there are 2 protons and 3 neutrons. Now after the emission, what happened? The total number of, right? So here Z is 5. After the emission also Z is should be 5 because the mass number doesn't change. What has happened is one neutron is transformed to, right? So one neutron is transformed to a photon. Right? So inside the atom, one neutron after beta minus emission, one neutron inside the atom is being transformed to a photon, proton, and emit a beta minus radiation plus the neutrino. And neutrino has is neutral. So here you can see the charge also same. So that is beta minus emission. So likewise in beta positive, positron is called positron emission. And in general, we can write positron emission. Yes. So X A Z after the emission of a positron, the number of mass number doesn't change. The atomic number would be decreased by 1. And neutrino is emitted. So here bar sign is not there. Right. So here what happens? Inside the element. So in beta minus emission, a neutron. And a neutron is transformed to a proton and emits the beta minus. So here here the opposite happens. Here number of protons in the element is decreased by 1. It is decreased by 1. So let's say proton initial one outside the tape, same particle having the mass number is 5. So what happens here? 1/4 proton is transformed to a neutron, remaining the mass number same, but the atomic number is now less. So here one proton is transformed to a neutron plus emitting positron and a neutrino. So here what happens inside the element under positron emission, beta plus emission. One proton is transformed to neutron. Right. Then gamma emissions. Finally, we have gamma emissions.
Let's say in beta plus emission, beta minus emission, what's the other particle? The one with the minus, with the bar sign, yeah.
That is called anti-neutrino.
Okay, in the other one, beta plus?
It is just neutrino. Neutrino. So just for now, just know what is, just get the idea. There are something called neutrino and anti-neutrino. Later we will discuss about that at the latter part of this section. For particle physics, we will study about this neutrino furthermore. So just for now, just know when a beta minus emission, antineutrino is formed, and in beta plus emission, neutrino is formed in addition to that. And so this is what happens inside the element. Inside the elements, a neutron is transformed to a proton emitting beta minus. Here, photon is transformed to a neutron emitting beta minus. Right. Then alpha emission is very easy. Alpha emission is very easy because alpha particle, alpha not a particle, it is a ray. That alpha ray, and it doesn't have any atomic number or mass number. 0, 0. It is a wave, just a wave. It is just a wave. It's just a wave. It is just a wave. So let's consider so boron having 5, 6, 12, and it initially emits beta minus particle plus an antineutrino. Right, so it would attain 6, 12, and this star represent this is unstable. That unstable carbon. That after beta minus emission, unstable element could be obtained as well, and an unstable element could be obtained. In that case, without changing anything, without changing either the atomic number or mass number, is excited. Right? Excited state is hashtag. This asterisk, this asterisk represent excited state. Right? It could be transformed to same element having 6, 12, having same atomic number, same mass number, and emits gamma. Right? So this is gamma. So this is neutrino, antineutrino. This is gamma ray. This is gamma ray. This is gamma ray. So gamma ray, the emission of gamma ray is very easy. No, doesn't change anything. Only the energy is decreased. And so this is actually energy. Energy, not a particle. Right? So gamma ray is not a particle, it just emits energy, right? Bringing an excited element into a more stable element. Right? And another example is cobalt 2760. Right? So it first decay into nickel. So this, any of this you don't have to, this equation you don't have to remember. What you have to remember is what happens here. Always the atomic number and both atomic number and mass number on both sides should be same. Okay? So nickel, it transforms 28, 60 emitting beta minus electron and antineutrino. And here this asterisk represent that nickel is in excited state. or unstable. That's same thing, excited state or unstable. So it would transform to a more stable state of nickel without changing the element by emitting just gamma ray. Right? Gamma ray. Right? So the emission of gamma ray is very easy. It does not change either the atomic number or uh, either the atomic number or either the atomic number or mass number. That's why emission of gamma rays do not change either the atomic number or mass number. Mass number, atomic number or mass number of the element. Atomic number or mass number of the element. Atomic number or mass number of the element. It would not change either the atomic number or mass number of the element. Only the energy would be decreased, right? Only the energy would be decreased. So here we can see what happens. First we have cobalt atom, then by beta minus emission, it comes to nickel excited state, and by emitting gamma, by gamma emission, it comes to a more stable state of same element nickel. Either the atomic number or mass number. Only the energy level is decreased. And so these are some examples of radioactive nuclei: cobalt, iron, sodium, uranium, and this denotes the mass number. 60 of mass number of cobalt, 555 is the mass number of iron. So you don't just these are just for knowledge. You don't like to memorize this. So before going into radioactive integration law, the first law that describes the number of. So what happens? The first equation we have. Is the first equation we have. So before going into that, you can take this down. Eddie, do you have any question until now? just talk about some basics equations. So you can consider this equation same as the somewhat similar to chemistry equation. And here, the atomic number and both uh, atomic number and mass number should be same on both side of the equation. Here, in all these equation, atomic number and mass number of both side of the equation are same, equal. Uh, yes, so you can take this down maybe.
Nothing, but
So first you can write down this. So just quickly take this down. You know, and when you finish, just let me know so I can scroll it up.
So could you scroll up a little bit? No, above that. So what are the X's near the lead block?
Sorry, can you ask it again? I didn't hear you.
The X's near the lead block.
X. This X. Uh, this X represent. Are you asking about this one? This one?
No, the ones near the lead block. The,
These just show that this area, surrounding area, is protected from gamma rays, from not gamma rays, from gamma rays as well as radiation. And so here the red uh, sample. The sample is this radioactive sample is kept inside this net, inside the net block. So there's a opening here. There's an opening here, and the radiation would be only emitted towards upward. Like this other region, the surrounding other region is just protected from radiation. That's what I denoted by this crosses. So the only opening is here, right? The only opening of the lead block is uh, uh, and so it means that the radiation is only allowed to go in an upward direction. And so all the other regions are just protected from this lead block barrier. And if this radiation is if this radioactive element is just kept in open space, then all the this is decrease. All the environment is exposed to the radiation. So that's why it is kept inside this lead block, so that only a specific direction is open. So only all the other uh, surrounding is protected. So that's why it is kept inside this lead block. So this process represent that this area is not affected to the radiation. So here both alpha and beta radiation are they are charged particles, whereas gamma rays it is neutral, uncharged. And alpha particle is considered as helium nucleus. It's equal to helium nucleus, and beta minus particle is equivalent to electron. Whereas beta plus particle is named as positron, having the same characteristic of the electron, but only difference is the charge is positive of the positron, and we know the electron is negative. The mass or the other physical parameters are same. Mass is same. The magnitude of charge is same. Here the penetrating ability of gamma rays are the highest. Then comes beta particles. Lowest is for alpha particles because alpha particles are somewhat bigger uh, than the other two. So they cannot penetrate through small spaces. Like gamma is just a wave. It's a wave, so it can a wave having very high frequency. High frequency means high amount of energy, so it can penetrate through the small phases, even through this very small phases, having the highest penetrating ability. And then here when alpha emission happens, when alpha particle is emitted, always the atomic number decreased by 2 and the mass number decreased by 4. So here another special point is only the alpha particles would change the mass number. Neither gamma particles, gamma rays, or beta particles could change mass number. Only the alpha particles, the emission of alpha particles could change the mass number.
You can scroll down. No, I need the beta negative emission.
So here beta emission would happen in two ways: beta minus emission and beta plus emission. So beta emissions only could change the atomic number, not the mass number. So these are just examples which we don't have to remember. But we have to know what happens when alpha emission happens and beta emissions happens. And finally, gamma emissions happens. In gamma emissions, uh, neither the atomic number or mass number changed, only the energy level. Energy is released by gamma emission, gamma ray emission.
And say the emitter anti-neutrino.
Sorry, emitter?
Anti-neutrino.
Yes.
That extra one is an antineutrino, or what is that?
Yes.
Anti-
Anti-neutron. Anti-neutron.
When you scroll down a little bit.
So here it is given in the above decay process, in addition to beta particles, another particle called antineutrino is emitted. But emitting a particle called antineutrino is required for that process to obey the law of conservation of energy and law of conservation of momentum. To obey those two laws, conservation of energy and conservation of momentum, the emission of antineutrino is required. So antineutrino is just uncharged fundamental particles. It's just an uncharged fundamental particle. But fundamental particles, we will discuss latter part of this section. So mainly there are 9 such particles. So here without the bar sign, it is neutrino. This is neutrino. This is neutrino. With bar sign, it is antineutrino. So during beta minus emission, what happened here is inside the atom, inside the element, a neutron is transformed to positron, increasing the atomic number. And in addition to that, beta minus particle and antineutrino is released.
Sir,
Whereas in
positron is a proton, right?
positron,
Is it a
sorry,
proton?
here neutron is transformed to proton. Yes, proton. Positron is not proton. Positron and proton are different things. The beta plus is called as positron. So this is called the positron. Beta plus positron. Beta plus particle is called the positron, whereas beta minus particle is called the uh, electron. Electron. This electron. Beta minus, beta plus is positron, and proton and positron are different particles. Positron is just the particle similar to electron, but having the opposite amount of charge. It is similar to electron, but the charge is positive. Positron is different. In positron, mass is very high than electron. Sorry, proton. Sorry, proton is different. In a proton, mass of the proton is higher than the positron. So they are not same. Two different particles. In beta plus emission, proton, and this P represent proton. Here P represent proton. N represent neutron. Neutron. Not neutrino, neutron. And although the pronunciation might be somewhat similar, they are different particles. Neutron and neutrino are different. Proton and positron are different. So in beta plus emission, proton is transformed to neutron, releasing beta plus positron and neutrino. Here during beta plus emission, the atomic number decrease by 1. Mass number remains same.
Okay.
Finally, gamma emission. Gamma emission pretty easy. Nothing changed, no atomic number or mass number, only the amount of energy, some portion of energy is released as gamma ray.
Here also there's an anti-neutrino.
No antineutrino. So here, this antineutrino is corresponding to the first emission. Here the first emission represent the beta minus emission. Beta minus emission, then after the beta minus emission, it forms the excited state of carbon. At excited state of carbon, this asterisk represent the excited state of the carbon atom. Then that excited state is transformed to a more stable state, releasing gamma ray. So that is denoted by the second expression. Excited state of carbon is transformed to a more stable state of carbon, just releasing gamma ray. Just releasing gamma ray is a neutrino. Sorry, antineutrino is released during the emission of beta minus particle. So initially, the boron is transformed to carbon by emitting beta minus particle in the antineutrino. Then the excited carbon, the again excited carbon with the asterisk, is then converted to more stable carbon plus gamma ray. So here neither the atomic number nor the mass number is changed during the gamma emission. So it is very easy. Nothing changed, only the energy level during gamma emission.
Done.
Lots of radioactive nuclei. I'll score some examples. Let us try to do this. The first question. Which one of the following statement made about X-rays and gamma rays not true? Gamma rays have shorter wavelengths than X-rays. Is it true? No, gamma rays have even higher frequency than X-rays. So gamma rays have gamma rays have shorter wavelengths than X-rays. It is correct. Gamma rays photons are charged, whereas X-ray photons are neutral. What about that? So they're asking about the wrong statement. X-ray more penetrating power than gamma rays, more power than X-rays. Both gamma and X-ray travel with the speed of light in vacuum. Both X-rays and gamma rays can be diffracted. This one is correct because the electromagnetic wave, so they can be they should obey the laws of or the properties of waves. So they should be diffracted. The wrong answer is second one. X-ray photons are charged. No, they are not charged. They are neutral as X-rays. Both X-rays and gamma rays, they are neutral charged. Which is not true. The gamma rays have more penetrating power than X-rays because gamma rays have higher energy than X-rays, and they have more penetrating power. Both gamma rays and X-rays travel with the speed of light in vacuum. That's correct. Both X-rays and gamma rays can be diffracted because that's also correct because they are waves. They should obey the properties of waves. One of the properties is diffraction. Second one. Which of the following properties is not common one for all three alpha, beta, and gamma rays? Carrying energy, so particle as well as wave nature. Ability of ionizing air. Being emitted by nucleus of an atom. Having a charge. Each one is not common property. So we know alpha rays and beta rays have charge because that's why they are diffracted. They are being shifted then subjected to both magnetic and electric field, whereas gamma rays, they are not affected by either magnetic or electric field. So especially if a particle is not affected by electric field, then it does not have any charge. So gamma rays not have charge. So which of property is not in common is having a charge. It's not common. For gamma rays, no charge. Then fourth one, an isotope of uranium 239. That is the mass number. 92 is the atomic number. Decays by the emission of beta particles. By the emission of beta particles. Which of the following responses gives the correct mass number and atomic number for the new nucleus form?
So is this emission of beta minus or beta plus?
Decays the emission of beta. Just go for decays the emission of beta. Which of the following response gives the correct mass number and atomic number for we have to go for beta minus particle. Should not beta particle. Which of the following response gives the correct mass number? Our atomic number for the new nucleus form. Mass number. The beta minus particle. Take beta minus particle. Normally, if it is given as beta, it is referred to beta minus particle. If it is given explicitly as a positron or beta positive, we have to go for the positive. Normally, mainly beta particles is equals to beta minus for the electron. So go for beta minus particle. So here mass number doesn't change. By beta emission, mass number doesn't change. Mass number doesn't change. Atomic number would be, what about the atomic number? By beta.
Plus one.
Yes. By beta minus emission, atomic number would be increased by 1. Atomic number would be increased by 1. So 239 is the mass number and 93 with atomic number. So answer should be 239 and 93. Fourth one should be the answer. Uh, 6 are also right. The radioactive element X having A of mass number and 86 of atomic number decays to a stable element of Y having 206 of mass number and 82 of atomic number after several alpha emissions. Only alpha emission. The value of A is
240.
240.
Yeah.
240. Uh, let's say we have 86. A goes to Y having 82, 206 plus only alpha emission. So alpha having 2 and 4 of atomic number and mass number. So let's say number is n. So here both sides, the atomic number and mass number should be same. So if I consider atomic number, 86 should be equal to 82 plus 2 into n. Then 4 is equal to n is equal to n is equal to 2. And considering the mass number also should be same on both sides. A is equal to 206 plus n into 4. So n we found as 2. So 2 into 4 which is 8. 240. Yes, correct. 240. Then try 7th as well. Radioactive thorium having atomic mass number 90, 234. The name is emits beta minus emission followed by an alpha emission. Followed by an alpha emission, the resulting nucleus will have at first emits 2 beta emissions. Yeah, actually this notation should be the other 2134 should be it should be 234 and 90. So 234 thorium 90 would decay to beta emissions, 2 beta emissions, beta minus emissions, and followed by an alpha emission, 1 alpha emission. Alpha emission, the resulting nucleus will have. What we have to do is just equate the atomic number and mass number of both sides.
Third one.
Third one, 90 protons and 140 neutrons. Right, so here we have this equation. So 2 beta minus emission plus 1 alpha emission. So I considered the mass number. The mass number is 234 on the left side, and on the right side of the equation is Z plus 4, because mass number is not changed by beta minus emission. Then I have Z is equal to 230. Z is equal to 130. This is the number of protons plus neutrons. Then considering the atomic number, 90 is equal A plus minus 2 plus 2. Yes, so A is equal 90. A is 90, which is the number of protons. That number of protons. Number of protons. Then to get the number of neutrons, just use this first equation. Number of neutrons is equal to 130 minus 90, which is 140. Yes, that one is correct. That one is the correct answer. So here, just important statement is only the alpha particle, only the alpha emission could, only the alpha emission could change the, only the alpha emission change the mass of a particle, right? Only the alpha emission could change the mass number of a particle, right? So today we learned some basic things of this alpha, like this radiation, radioactivity is found by Henry Becquerel and then named by uh, Marie Curie. So mainly there are three radiations could happen: alpha particles, beta particles, and gamma particles. So these characteristics should be known. Alpha particles, uh, they are similar to the nucleus of helium, whereas beta particle is similar to the electron, beta minus particle, and beta positive particle is named as positron. Then gamma is not a particle, it is a wave. Basically a wave, more biased towards the nature of wave. So that's why it is called as gamma ray, which has the highest penetrating ability. The gamma alpha ray has the lowest penetrating ability. Then this decay, radioactive decay, what happens in each emission. Under each emission of alpha, beta, and gamma, we looked at. Next comes actually some equations called disintegration law. Yes, that is a basic equation we have. Then we have something called half-life. Basically, there would be just two equations mainly. Mainly two equations. S and the particle physics part left. So we'll we will go for that in the next session. So thank you.